Bismillahirrahmanirrahim. Before dissertation defense is commenced, please set up your mobile phone into silent mode, and it is not allowed to take picture or photo during this dissertation defense, except who had already had permission from SPS ITB, since it will potentially disturb this process. Ladies and gentlemen, Assalamualaikum warahmatullahi wabarakatuh. Greetings for all of us. Bismillahirrahmanirrahim. I hereby declare this dissertation defense is open. This dissertation defense is held to provide an opportunity to doctoral candidate Selvi Lukman to deliver her dissertation research on this timely subject entitled New Empirical Path Loss Formula for High-Speed Rail Channel Modeling Using Meta-Heuristic Optimization, and also to answer all questions or defend her dissertation against critics or comments in this session. The doctoral candidate has been doing her doctoral research under supervision of the promoter teams as follows. The first one is Professor Dr. Insinyur Yul Yunaswin MSc DIC from ITB as Chief of Promoters. Second one is Professor Insinyur Indra Yulianto PhD from ITB as Chief Co-Promoter. And the third one is Professor Boai PhD from Beijing Jiatong University, China. And he will join this presentation by online as co-promoters. And also the examiners for this session consisting Dr. Augie Widyo Triatmo, STMT from ITB will join this presentation by online. And then Dr. Irma Zakia, STMSC from ITB. And then also Professor Insinyur Kamantio Hendran Toro, Master Engineering PhD from Institut Teknologi 10 November Surabaya. Ladies and gentlemen, next I would like to ask the Chief Promoter, Professor Dr. Insinyur Yul Yunaswin, MSc DIC, to deliver the curriculum vitae for the doctoral candidate, and then also to convey the academic accountability regarding the acceptance of this dissertation. Okay, please.
Yes, thank you, Pak. Miss Selvi Lukman was born in Bandung, 22nd of September, 1975. He started his senior high school and then finished in 1994 in St. Leonhard Gymnasium in Aachen, Germany, and then continues his study in University of Jenderal Ahmad Yani in Cimahi in 2016 in the field of electrical engineering. And then she came to Institut Teknologi Bandung and finished his degree, Master of Engineering Physics in 2019, and then continued with her PhD in Department of Engineering Physics, ITB, and finished her study supposed to be today, 2023. Some of working experience, he was working in PT Cheong Song Indonesia as an assistant to the CAO, 1996 to 2000, and then became the technical director of Selvi General Techniques from 2000 until now. He's also a part-time lecturer at the University of General Ahmadiyani since 2019 until now. Shall I continue?
Yes.
Yes.
Please continue directly.
Okay, so this is the academic accountability report of Ms. Selvi Lukman with her dissertation title, New Empirical Pathless Formula for High-Speed Rail Channel Modeling Using Meta-Heuristics Optimization. During the doctoral program of engineering physics in ITB, Ms. Selvi Lukman has conducted her research entitled New Empirical Pathless Formula for High-Speed Rail Channel Modeling Using Meta-Heuristic Optimization. This research is a joint collaboration between Beijing Jiaotong University in China and Institut Teknologi Bandung, in particular with the National Center for Sustainable Transportation Technology, ITB. As the channel modeling for high-speed rail is fundamental to design a reliable wireless communication system, large-scale and small-scale fading are important for the design, performance evaluation, and parameter optimization of high-speed railway wireless communication system. The primary concern in the study is the investigation of path loss for high-speed railway, which contribute to large-scale fading. The new approach of conducting the path loss prediction for high-speed railway has been introduced. New empirical path loss model for high-speed railway to be utilized in free space and urban or suburban propagation have been proposed. The state-of-the-art path loss model of the high-speed railway were then validated using meta-heuristic optimization techniques, which has never been investigated in any existing literatures. The initial procedures in her study address a validation procedure of path loss measurement for high-speed railway, which dataset was provided by the Beijing Jiaotong University using the naive Bayes classification methods. This procedure is conducted because the new empirical models will rely upon the measurements. Afterwards, the model will constructed and integrated with the data sets. The first model is based from the free space propagation characteristic, assuming the transceiver are located in otherwise empty environments. However, when this model is not sufficient enough to mitigate the losses, another path loss is introduced. The two-ray ground reflection path loss model for high-speed railway was also in order to obtain the more reliable model. This model assumed the combination of direct signal path and reflected path from the Earth. Both of these path loss models were then validated by utilizing the meta-heuristic optimization techniques. The capability of the meta-heuristic optimization techniques has been proven to be robust in obtaining the unknown parameter values, where physical phenomena must be taken into account in a very dynamic system such as high-speed railway. As both models comprised the corresponding losses of high-speed railway's unique characteristic, the spatial MIMO antenna for high-speed railway has been specially also designed, in which its gain become the constant in the constructed path loss models. The final stage of hemisphere research work conveys the power link budgets for high-speed railway to be utilized in low and high frequency spectrums. The dataset is once again optimized using the combination of particle swarm optimization and the coefficient relation method in order to constrain the technical parameters in the power link budget so the obtained path loss model are in the range of observation. Furthermore, in low frequency spectrum, correction factor are capitulated by utilizing a point-to-point least path loss model, satisfying result of received signal levels in power link budget for both allocated frequency spectrum and propagation were finally achieved. Unfortunately, ultimately, the design power link budgets are readily to be utilized by network designers to deploy the frequency planning and optimal base station for high-speed railway in order to achieve its best performance. The output of this research have been summarized in some publications which have been fulfilled the criteria Q1, Q2, Q3, international journals, some international conferences, as well as under process patents and copyrights. Above mentioned points are the basis for the supervisors, consideration in accepting the dissertation of Ms. Selvi Lukman, and it is therefore Ms. Selvi Lukman is ready to be put forward in her final doctoral defense. That's all. Thank you.
Okay, thank you, Mr. Chief Promoter. Now, please kindly invite the doctoral candidate to attend in this meeting. Okay, doctoral candidate, are you healthy enough to perform this dissertation defense?
Yes, I am.
You have the opportunity to present your dissertation research within maximum 20 minutes.
Thank
Please,
you.
time yours.
Thank you. Good morning, all respected professors. Thank you for attending my final self-defense this morning. I'm proud to present to you my research entitled the new empirical path loss formula for high-speed rail channel modeling using meta-heuristic optimization. First of all, I would like to thank the Board of Supervisory, Professor Yunus Nasarudin, Professor Boai, and Professor Endra Julianto for their restless effort. My name is Selvi Lukman. I'm proud to present to you my presentation this morning, and I'm going to start with the sorry. Sorry, it's not working. Iya, udah. Yang mau. Yang. Sorry, must wait a little bit because of the pointer doesn't work. Okay. The outline of this morning presentation, we're going to start the research background and then to the research problem and the research contribution. And then I'm going to solve the uncertainties of high-speed rail path loss measurement using naive Bayes. And then we proceed to I'm proposing a path loss model to be utilized in free space propagation, followed to another path loss model to be utilized in urban and suburban propagation. And then I'm going to show you the design and simulation of power link budget in which the proposed path loss models are calculated into it. And then after this, we have a conclusion and remarks are drawn in the end of this presentation. Okay, let's see here. This is how Indonesia must face the severe public transportation problem. It may include the public transportation problem of saturation. It happens when the number of cars is more than the roadway can support. And then we have a problem of construction. It may include installing traffic lights, creating one-way streets, and adding more lanes to the highway. And also we must face the problem of accidents because car accidents block traffic flow for many reasons. And this problem is also growing leaps and bounds in developing countries like Indonesia. Therefore, high-speed rail provides many benefits as it boosts economic in many ways. It is safer than driving. It can reduce our dependence on foreign oil and congestion also. It is more efficient in time consuming and less smoke in the city as well. Now I'm going to show you a short video about our upcoming high-speed rail with only like Jakarta-Bandung, 36 minutes. We can observe how the multi-path propagation and a typical scenario of viaduct here in our small videos. From here, I'm going to show you that Indonesia adapt the future railway mobile communication system, which is a platform for unified voice and data communication for modern railway application. It is a platform for the previous GSMR. It is easily to be integrated to the higher allocated spectrum. And to ensure the reliability of the FRMCS system, we require what we call the channel modeling. And in the channel modeling, the channel modeling defines a mathematical equation about how the signal is behaved, and it is classified into the outdoor channel model and the indoor channel model. And the outdoor channel model, the signal is propagating, they must face the multi-path components. And whenever for the mobile realization to do high-speed rail, they must face the line of sight scenario and non-line of sight scenario. Meanwhile, in the indoor channel modeling, the signal is propagating from the mobile relay station to the mobile station, which is located inside the high-speed rail itself. So I must say the key objectives why we are adapting this FRMCS system is to mitigate the obsolescence of narrowband barrier technologies in order to upkeep with modern telecom infrastructures. This is required for more bandwidth to support advanced features such as maximum standardization like 3GPP and onward to fully support train control, security, and safety. So from here, I can comprehend my research problem like this. Indonesia adapt the future railway communication system in which we require a reliable channel modeling. Therefore, the study of path loss becomes very prominent. And there are two supporting technologies for the reliable transmissibility, what we call the MIMO antenna systems and the small cells, in order to achieve the optimal power link budget to be utilized by the network designers. In figure number 2 here, I'm going to show you the two supporting technologies for FRMCS. We can see here when the GSM macro cell is integrated to the higher spectrum frequency, you can say like 4G LTE or 5GR, you require an additional capacity in the form of small cells coverage. And we can observe in the antenna installed in the GSM macro cell, which is still utilize a traditional antenna system. When you are using a higher spectral frequency, you require a MIMO antenna system, which is abbreviated from the MIMO input and MIMO antenna system to ensure your reliability. Now I'm going to give you a comparison between the traditional path loss prediction and the machine learning type path loss prediction. For example, in the traditional path loss prediction, I have a factor of signal attenuation, signal interferences, signal power loss, and external reference system, and also the propagation type. Upon this factor, I have to conduct a measurement and intensive research, and then I analyze the attenuation and curving plot. And then I can summarize the formulation. Accordingly, Okumura, Hatawa, Visikagami model has already conducted that, and there are some inaccuracies of those models. Therefore, we have to conduct an error recognition and correction mechanism to those errors. Meanwhile, the utilization of machine learning provides many benefits. We can see here in the machine learning path loss prediction, we require loads of data set, comprises the path loss observation and corresponding features, and then we conduct the data cleaning. And after the pre-processed data set ready, we can do the data splitting. We can do it like 80 to 30 or 70 to 30. It's just what your convenience would like. And this is where the learning algorithm is injected. You can use SVM, SVR, or artificial neural network. And then we have a train model, comprises the estimation function and parameter optimization. And then I can have a predicted path loss values. This approach is very accurate. Unfortunately, there are some drawbacks too. One of them, we require more data set because more data set means the more reliable your model will be. And we will never really know which parameters that contributes the most to your path loss values. Therefore, in this research, I'm going to show you priorly in the simple link budget I designed for high-speed rail, you can see that when the signal is attenuated from the transmitter to the receiver, I'm going to need a path loss values. And in my research, it comes from the optimized path loss values. And let's see about this diagram in figure number 6. This is the path loss prediction based on meta-heuristic optimization technique. Priorly, I have to propose my path loss models. And in my model, there are some unknown parameters that I have to conduct. And this is a really the most impossible one to conduct in the field measurement. Therefore, I'm going to apply resolve by using the meta-heuristic optimization techniques. But priorly, I'm going to need an input path data measurement to be injected to my proposed path loss models. And this input path loss data measurement was given from the Beijing Jiaotong University. And then I observed the model really well. And I must say that my model is correct if I have a very minimized error. And also an output data path loss model has come to the nearest adjustment with the input path loss data measurement. So from here, I can comprehend the research procedure that I conduct in my doctoral research. First of all, I'm doing the validation using naive bias. This procedure is very important because upon this procedure, I'm going to underline my path loss model identification for free space and two-ray ground reflection. And then in my model, I'm going to need a constant that must sufficient enough to mitigate all the losses. That's why I'm designing and simulate an antenna MIMO using CST Microwave Studio. And then I'm going to validate the path loss model using meta-heuristic optimization technique. And the design analysis and simulation of power link budget can be established where the path loss values are going to be included in it. Okay, now I'm going to start this off with step number 1. In this part, there are 3 factors that must be under investigation. Firstly, we have a factor of path loss, the measurement, and artificial intelligence. And naive bias is being put in the middle because this is the utilized machine learning method that I'm using. And this is the common formulation of naive bias. The achievement would be the prediction of binary result in this term, accurate measurement or inaccurate measurement. And this is where all the data preprocess is located under the assumption of independence to each other. So let's see from the raw data set that was given from Beijing Jiaotong University, I apply the data preprocessing to be put in probability B, and I apply the Gaussian naive bias classifier. I can have a performance indicator then in the form of confusion matrix and the prediction of the binary result. And this is the performance of naive bias in validating my path loss measurement. First of all, you can see that I have a yielded accuracy 92.36%. This value is really high because machine learning usually tolerable like 88%. Although, and I have a precision 1. It means that if you conduct the validation all over again, I can still make sure I have still same number of precision, which is 1. Even though there is a trade-off with the recall number, which is 0.43. That's why I'm adding another performance indicator, which we call the F1 score. It is a harmonic bias between the precision and recall. And additionally, I added an area under curve receiver operating characteristic that is 1. Area under curve precision recall gain that is 0.95, which is classified as the best in this table. And you can see in the white area beyond the curve, we can see that naive bias has successfully validated the path loss measurement accordingly. From here, I'm going to propose you my path loss model to be utilized in high-speed train under the free space propagation in the viaduct scenario. And this scenario is chosen because this is where the signal is free from attenuation and obstruction. And in my path loss models, you can see this is the model that I propose. This is where the measurement data set that has been validated is located, which is equal to 92.45 plus 20 log frequency carrier plus path loss D0 plus 10 gamma log divided by D0 plus X sigma plus Doktor frequency plus vehicle penetration loss minus 14.89. As you can see, there are 3 unknown parameters here. I notified them as red, and I'm going to change the terminologies into X1, X2, and X3, having visually iterized when the iteration begins. These are the unknown parameters that we must find in using meta-heuristic optimization technique. But let's firstly define one by one the meaning of each parameter. Firstly, we have 92.45. This is the reference loss constant when distance measured in kilometer, when the frequency carrier in gigahertz. The distance is the observation range, 0 kilometer to 2 kilometer. The frequency carrier would be high with its 26 gigahertz. The path loss D0 describe all path loss values from close-in reference distance as receiver power reference points where average path loss are determined. You can say this in a simple term. This is where the signals begin to attenuate. And then after this, we have gamma, which is the path loss exponent is put initially to, and X sigma, which is a last gilding and shadowing. And then we have a frequency Doppler, which is a non-linear equation, and the values are dependent on the corresponding distance. And then we have 220 to 25, which is the maximum vehicle penetration loss, and the 14.89, which is the gain antenna MIMO 2x2 from the simulation using CST Microwave Studio. Now, firstly, let's talk about the path loss exponent first. This is a parameter indicating the rate at which the receive signal level decreases with distance. And this is the typical path loss exponent for many kind of environment. Let's say free space initially is 2, and we have a value for urban and suburban, indoor line of sight, and obstruction in building and factor is 2. But for high-speed rail, we will find out later how it can be achieved. Now, let's see here. Let's start validate the model, but firstly, I'm going to show you about the MIMO antenna system that I conduct in this research. Firstly, this is the manual calculation of a defective ground structure antenna, one element. And if I configure the antenna like this, I'm using RT Duroid 5880 because it is easily to be fabricated. And when I feed it with a microstrip feeding line, we can see the movement of the electromagnetic beam, and I have the gain would be 14.89 decibel. This value is very meaningful because based on this gain is sufficient enough to mitigate all the losses from my path loss values, and also it can bridge the low and high frequency spectrum of high-speed rail. Now from here, I'm going to show you how I'm using the meta heuristic. Firstly, I'm going to use the traditional one, which we call the generalized reduced gradient. Let's see in the third space from GRG, all the candidate solution one by one and step by step are trying to find its optimal point. Let's say the 13 is the optimal point by doing some steps in Jacobian matrix. And whenever they must face the constraint that I put in the algorithm, they must automatically reverse themselves in. As you can see that GRG has followed the dynamic scenario of high-speed rail when the distance is 230, when the path loss is 120. And these are the candidate solution achieved by GRG. From GRG, I'm using an evolutionary algorithm, which is the famous genetic algorithm. While GRG is trying to find its optimum point step by step, in GA, they are all spread it out in the search space like this. One point indicates the candidate solution that must be converted to the binary system. And this is where the parent selection, crossover, mutation, replacement, and best chromosomes are chosen. As you can see, the GA has already validated the path loss model when the distance is 219, when the path loss is 120. And these are the candidate solution achieved by GA. From GA, I'm using another meta heuristic, what we call the particle swarm optimization. So here we have two kind of terminologies: what is the best position and what is the best velocity. And of course, there are some number of control parameters like inertia weight, coefficient relation, how many iterations do you want to conduct. And you see that PSO has successfully validated the model when the distance 194, when the path loss 119, and these are the candidate solution achieved by PSO. From PSO, I am using CAPSO. CAPSO is an improved PSO because it uses only the global best without individual best solution to reduce randomness. Not to forget to mention that in CAPSO, I'm injecting the Newton law of motion to iterate the process really fast. But you can see that the performance of CAPSO, it converges when the distance is 224, when the path loss is 120, and these are the candidate solution achieved by CAPSO. From CAPSO, I'm using FPA. This is a more up-to-date algorithm. We can see in flower pollination algorithm, we have two kinds of pollinators, what we call abiotic if the pollinators is the wind, biotic if the insects are the wind. And then we have type of pollinators. We have self-pollination with the same flower, self-pollination with different flower of the same plant, and cross-pollination with different plant. And based on these pictures, there are 5 rules of FPA that must be considered. Firstly, the biotic pollination and cross-pollination is a global pollination, with carried by the pollinators. We can call the pollinators as the leaf-5 flight. And the abiotic pollination and self-pollination are considered as local pollination. And insects as pollinators are equivalent to the flower constancy with reproduction probability proportional to the involved similarity of the two flowers. And then we have the local pollination and global pollination are controlled by this switch probability. You can choose either 0 or 1. And in the global pollination, in the global pollination and the local pollination are implemented based on the switch probability. And you see, FPA has made its convergence when the distance is 185 and the path loss is 119. And these are the candidate solution achieved by FPA. From FPA, I'm using another optimization, what we call the whale optimization algorithm. This is mimicking the hunting behavior of the humpback whales. Whenever there are three terminologies we have to consider. Firstly, what we call the in logarithmic spiral, it is searching for the prey, and the bubble nut attacking what we call the exploitation phase, and searching for prey is the exploration phase. And this whale optimization can already validate the path loss model when the distance is 229, when the path loss is 120. And these are the candidate solution achieved by FPA. From here, I'm going to show the comparison of those meta-heuristic optimization for free space propagation. From the 6 optimization technique, it is FPA that chosen to be acceptable to be put back in the equation because it converges faster than the other optimization techniques. And therefore, let's see about the iteration of path loss exponent. In high-speed rail, in my research, the path loss exponent is achieved by doing averaging of each batches of iteration. One batch is like 500 times. And we can see I can put gamma as 2 as the average path loss exponent in the equation. And this is the candidate solution achieved by FPA that is acceptable to be put back in the equation. And this one, we have to calculate it with the distance, correspondent distance. So now we have a complete unknown parameters that's been completed by using FPA. And then in step number 3, I'm going to show you another proposed model. This model is more reliable and elastic model. It can predict large signal strength over several kilometers with minimum transmitter like 50 meter. This one has to be 50 meter. And practically, the separation between base station and the mobile should be 10 times high transmitter plus high receiver, but ideally, it's just more than high transmitter plus high receiver is enough. And in this model, we assume 2 incoming signals, what we call the line of sight scenario, and the Earth reflected once, assuming the Earth is flat and no stepping inclines. And these are the models for this, for urban and suburban environment. And there are some additional parameters too. Here you can see that there are again 3 unknown parameters that must be resolved by using meta-heuristic optimization. And I'm using what we call the GBN and FPA in validating the path loss model of two-ray ground reflection. FPA has priorly successfully validated the model. That's why I'm choosing to use FPA again. And it successfully validated the model in 263 when the path loss is 120. And these are the candidate solution achieved by FPA for urban and suburban scenario. And I'm using the GBNN2, which is abbreviated from gray box neural network. And in the distance 297 and the path loss 120, we have achieved the candidate solution. What makes unique with GBN, and GBN is a greedy algorithm. We require loads of data set, but only with a little data set, it can perform very good. You can imagine if we have more data set, you can increase your accuracy as well. Now let's see the comparison of GBN and FPA in validating the two-ray ground reflection. We can see these are the candidate solution achieved by FPA, and when the distance is 263 and the path loss is 120, it's successfully validated then. Now let's notice about 4.14. This is the path loss exponent for urban and suburban, and it comes from the iteration. I'm doing like 5 batches of iteration. Each of them would be like 500 trial times. From here, I'm going to show you the design and simulate link budget. But before that, I'm going to show you that I'm doing another optimization, this one using PSO, because I have to make sure that my path loss models are in the observation range. And another one, I have to use a correlation coefficient to show the associated strength of each variables. And this is the path loss models to be utilized for free space propagation in high frequency spectrum. Let's check it out together. We have a parameter for transmitter. What makes the difference is the antenna height should be 30 because this is simple viaduct scenario. The 14.89 comes from the simulation. And this is the environment characteristic that has been included to the model. And the gamma is 2, the constant will be 92.5. This is the VPL is located. This is the parameter receiver. You can see the gain will be 6.19, and the cable loss and antenna height comes from the textbook because the antenna should be counted from here to the antenna that installed in the high-speed rail. And this is where the optimization result is located. We have the path loss D0, we have X sigma, class scale fade shading and fading, and Doppler frequency that must be calculated with distance. And if I click the calculate, I have the optimized path loss 143, which is in the observation range, and the receive signal level will be minus 90, which is indicated into the good and into the average, which is mediocre only. But let's compare it with the two-ray ground reflection. What makes a difference with this path loss model is the antenna height should be 50. And the gamma would be 4.14. And the constant should be 92.5. And this is the same optimization result. And if I click the calculate, I have the optimized path loss values. The resistance level would be minus 555, which is in the best specification. And next, I'm going to show you, this is the parameters, the list of parameters, average and best, as I have shown you before in the previous link budget. The optimized values and the resistance signal level that I have achieved is average, and for two-ray ground reflection, the optimized will be 180, the resistance signal level will be indicated as the best. Now for the low frequency spectrum, what makes a difference with the low frequency spectrum is I'm gonna use the constant 32.5, and the carrier frequency will be 900 megahertz. And also what makes a difference that we must put the least path loss models, which is point-to-point models. And the optimized path loss values and the resistance signal level for free space propagation is good. But in two-ray ground reflection, what makes a difference is we have to use gamma 4.14. So there we have a optimized path loss for 140, and the resistance signal level will be minus 87. Now we come to the conclusion and remarks. Firstly, the FRMCS of high-speed rail requires a comprehensive analysis of channel modeling, in which the stadia path loss must be thoroughly analyzed. The Curie validation firstly conducted by using naive bias because the free space propagation model and the two-ray ground reflection model will be underlined with this procedure. The constant of a gain antenna is achieved from the design and simulation of a MIMO antenna, and the proposed model are validated by using the meta-heuristic optimization. And then the optimal link budget is further designed and simulated, in which the path loss values will be capitulated to the receive signal level in the high-speed rail will be finally acquired. And then the optimal link budget can now readily used by the network designers of high-speed rail to plan the cell coverage, new frequency setup, and base station infrastructure planning. So this is the end of my presentation. Thank you very much. I'm open to take some comments. Thank you.
Okay, thank you, Selvi, Lukman. Yeah, high speed presentation. Okay, so you have some time maybe to have a seat and also to have drinks maybe before we continue for the discussion.
Okay, thank you. I'm ready.
Yeah. Ladies and gentlemen, now we are going to continue with question and answer. First, I would like to ask to external examiner Professor Insinyur Kamantio Hendrantoro, Master Engineering PhD from ITS, to deliver some question or comment. Okay, please, time yours.
Thank you, Mr. Chairman. Good morning, to Selvi.
Thank you,
Okay.
Professor.
Yeah, first of all, I would like to congratulate you for reaching this final stage of your doctoral program. Yeah.
Okay.
Okay, I hope everything is going fine today. Yeah.
Thank you.
Okay, so I have basically two big questions. Yeah, the first one is about the HSR communication systems, because it's not really explained in detail in your dissertation. Yeah. So okay, so in a communication system, there are at least two parties, yeah, communicating with each other. At least there is one transmitter and at least also one transmitter. Yeah. So in HSR communications, who are these two parties? So one is the base station, I understand. So what is the other one?
Other one would be the high-speed rail itself.
Which is so where is the okay, so let's say it's a receiver. Where is the receiver located?
The receiver is located usually in the high-speed rail itself, and because the antenna is installed there.
It's on the rooftop of a coach.
Yes.
Every coach, or only one coach for like a train?
I assume this is only the head of the high-speed
The head.
rail. the
Okay.
head.
Okay, good. Okay, so what about the passengers inside the coach itself?
Okay, the passengers inside the high-speed rail is considered as a small-scale fading, as I have explained before. It includes the small-scale fading because the signal is propagating from the mobile relay station that is laid along of the track to the mobile station, which is inside the high-speed rail, what we call the indoor channel modeling.
Yeah, so that means the passengers actually communicates with the kind of access point.
Yes, they have an access
On the rooftop or inside the coach itself. Yeah.
Yes.
So they are not communicating directly with the base station. Is that right?
Yes, it's
Okay.
only with the mobile relay station, which is located as mini mobile station.
Okay. 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 Good. So in this case, because you are looking at the communications between the base station and the transceiver on the rooftop of the coach, the head coach, who will be the co-channel interferers?
All the co-channels will be as I have put in a candidate solution, it would be the large scale fading and shadowing that will be the interference. That's why the value is really high, because I summarized the large scale fading and shadowing into the candidate solution number 2.
Okay, so you were talking about the fading, yeah,
Yes.
the fading that happens in the channel,
Yeah.
Which is usually caused by multiple paths,
Yes.
multiple path
Yeah, because
propagation.
I compress it into one
Okay,
candidate
but
solution.
isn't there any other transmitter around that also transmits a signal at exactly the same frequency as the signal transmitted by the base station, so that there will be interference?
Yes, there should be. Therefore, I think the Doppler shift must be investigated.
Yeah,
must be
but okay,
compensated.
Doppler shift, fading, and so on are the phenomenon of the natural phenomena, right? What I'm talking about is disturbance from other transmitters at the same frequency. So is there anything like that in your analysis, or in HSR communication systems?
Actually, your question is about we have to do the modulation, because because what I'm talking is about the large scale fading when we have several kilometers away, and when there are some small distances from other transmitter, it should be located as a small scale fading. Therefore, we have another different of mitigation. Maybe methods of equalization or adaptive modulation and something like that, in order to mitigate those obstruction and interferences, that kind of obstruction.
Okay, so because I'm not really familiar with HSR communication systems, so is there any kind of cellular scheme applied in HSR communication systems?
Yes, actually, cellular is included too, but this one is for automatic train control.
Yeah. Okay. So the cellular systems, cellular network, actually, yeah, is usually applied because we would like to reuse the same frequency to reduce interference effects. So are you aware of that?
Yes. Yes.
Okay.
Of course.
Okay. Good.
Maybe we can add some Wi-Fi repeaters inside the trains to ensure our transmission link too.
Okay. Okay. So the base station used in the HSR communication systems, is it exclusively used only by like for the high-speed railways, or is it also shared with non-HSR
No,
users?
it's only for the high.
Oh, okay. So
rail.
there is no interference from other systems, actually. Yeah.
Yep, it's only for high speed rail.
Okay. So, but I think you also mentioned earlier in your presentation that there is the advanced communication systems, which is as proposed or standardized by 3GPP release 16. I think you mentioned that.
Yes,
Yeah.
yes.
R16.
Yeah.
So does HSR communication systems also use release 16 in like in the standardization?
Okay, the GSMR uses the GSMR because
Okay.
actually this is the FRMC system is the platform for the first. We are using GSMR actually in
Okay.
Indonesia, and it has fully supported the 3GPP. But when it is migrated, I can the module should be moved to the higher integrated spectrum.
Okay. So when you try to model the radio channel, I think you also should understand the waveform, for example, yeah, the modulated carrier signals, yeah, in order to understand, let's say the symbol rates, for example, the data rate, and aside from that is also the bandwidth required by the signal. So do you know what kind of waveform, what kind of modulation scheme is used?
OFDM.
OFDM, okay. So how large is the bandwidth required?
Actually, OFDM is not part of this research because I'm not investigating that small scale.
Yeah. My question is probably related later with my other question about the antenna, because in designing the antenna, you specify a required bandwidth, right?
Yep.
That means the required bandwidth for the antenna should also meet the requirement for the UFDM, right?
Yes, yes.
Okay, so how much is the bandwidth of the antenna that you designed?
I'm using like the 26. This is for the 26.
That's the carrier frequency, right?
Yeah.
I'm asking about the bandwidth, the spectral width.
The spectral. I have to open my.
Okay, so I think it's about 500 megahertz, perhaps.
Yes, about 900 or 500. I have to
Oh,
read
okay.
again.
Okay.
To read it again.
So which means the antenna is prepared, is designed, yeah, to handle that wide of the bandwidth, yeah, of the spectrum used by the signal, right?
Yeah.
Okay. Do you know how large is the data traffic that would be sent through an HSR communication systems, for example?
Actually, my data was given as a secondary data set from Beijing Jiaotong University. This is like for my observation range is only for 0 kilometer to 2 kilometers. It's like not very much data.
Okay.
So I'm very working with a very small data.
Okay. Okay then. So you said before that the waveform or the modulation scheme is OFDM, right?
Yep.
And OFDM signals employ multiple subcarriers, right?
Yeah.
And between subcarriers, there are spacings, frequency spacings.
Yep.
Yeah. And you also mentioned in your dissertation about the Doppler effect.
Yes.
So do you think an OFDM signals sensitive to Doppler effect?
Yes, because the Doppler will destroy the orthogonality of subcarrier systems. That's why the mitigation of small scale fading must be analyzed too in maybe in another field of project.
Okay, so now if, for example, we take the OFDM specifications taken from, let's say, release 16, for example, yeah, how large Doppler effect should be allowed? Yeah.
Okay. For my model,
Yes.
I assume it is constant because in my model I assume that the high speed rate is just running straight without any turning, or we are not passing tunnel, we are not passing steep inclines or something like that. So I assume the constant would be very small and
But you can actually calculate it, right? Because you know, let's say the maximum velocity of the railway, yeah. Right. And
yeah.
so
yeah. Actually, The velocity is very tuned. It's very tuned. You will never know how much the velocity will be tuned because it's also dependent with the propagation along you. Because when you come to the suburban, you have to slow down, and with a free space, you can just speed your train. So therefore, it's really tuned. But I assume in my model, in the Fiat scenario, the Doppler would be small and very constant, and it is calculated with the corresponding distance.
Okay. So what is the maximum speed of a railway train, a high-speed train?
High speed train, you can run like 350, like in Indonesia, 350. But
Kilometer per hour.
it's
Okay.
the power.
Okay. Okay. So I would like to move on to my next set of questions. Yeah. This is about the antenna design. So okay, can you show slide 19?
Yes.
Okay, so you can actually you can answer more relaxed if you want.
Thank you.
Okay, so okay, so I'm interested in the shape of the antenna design.
Yeah.
My first question is that antenna, or will that antenna be installed in the base station or in the coach?
This antenna should be installed in the base station.
Okay.
Okay,
so how many antennas are actually there?
100 per radiating elements. 112. Yeah.
So how are you going to fit that antenna? Do you need only one fit or 112 fitting?
Okay, has to be. I don't picture it here, but as I'm sorry, I don't recognize the question because
Okay, so
I'm not
so there are 112 elements.
elements. Yeah.
Are those elements operating in the phased array mode?
Active array. It is
Yeah,
more
so it's an array, right?
yes.
So in fact, it is not a MIMO system, right?
Active. This is the MIMO, but it is an active antenna array.
Yeah, so it is actually related to my question before. How many feeder actually you need to operate that antenna? Only one, so that that one input will be split into, let's say, 112 elements, or you actually need 112 feeders?
I think this is just a simulation because I don't install it
Okay.
Independently with the
Okay.
base station. I think it is only one because it
Only
is
one.
simulated only.
Okay, so if it's only using one feeder, that means it's actually a single antenna. Yeah. For operation in MIMO scheme, you will need more than one antenna, several antennas like that.
Mm.
Yeah. Okay, so it's only one. So what is the dimension of that?
This is the manual calculation.
The width and the
The one
length?
element.
No, actually the whole thing. What is the dimension? Because I think it's not there.
Yeah, it is not there because it is not written in the simulation, but the simulation doesn't account the measurement of the dimension. It's only show you the direction of the electronic beam.
Okay, but I assume it's not very large, yeah, because you're using 26 gigahertz, which means the wavelength is probably in the order of 1 centimeter, I think.
Yep.
At least the it says, I think 7.9 plus 4, which means about 1.5, or let's say 2 centimeters perhaps, yeah. And,
yes, it's like 13 centimeters.
okay, then you have you know, like the width probably 20 or 30 centimeters.
Yep.
Yeah, for that. Okay, that means if you actually, my question is more about its application for MIMO, yeah. Because I think you mentioned in your dissertation, the HSR communications requires massive MIMO.
Massive MIMO.
Right?
It should be more than this.
Yeah,
this
so
element must have massive MIMO in the
yeah,
base station.
do you know why HSR communications require massive MIMO?
Yes, to ensure the transmission link because it has an ability of beamforming and multiplexing as it can carry data simultaneously over frequency similar path.
Okay, your answer is correct. So MIMO is used, massive MIMO, yeah, is used because of its beamforming capability, but also for multiplexing, yes, spatial multiplexing. Okay, so so that's only one phased array that you show there with 112 elements. Now, how much gain improvement, antenna gain improvement you obtained by using 112 elements?
I have achieved like gain 14.89, and one of the literatures that I have read that to mitigate to bridge low and high frequency system, as one of the literature said, I have to achieve more than 10 decibel for that. So I think I have gained 14.89 is sufficient enough to mitigate all the losses and for bridging the low and high frequency spectrum.
Okay, okay, but actually, if you have 112 elements and all of those are looking at the same direction, I mean, it's let's say scanning or facing the broadside direction, then you will have a full constructive addition of waveforms, yeah, or electromagnetic waves, yeah. Which means at least you have 112 in total constructive addition of the electromagnetic waves. So if we change that, convert that into decibel, then I think you should have more than 14.89, right?
Okay, this is actually from the simulation,
From the simulation.
but that is very meaningful. That
Okay.
makes my path loss values really good then.
Okay, okay. Okay, so now if we see the radiation pattern, yeah, so in that radiation pattern we can see there are at least let's say it's probably four beams, yeah, four big beams.
Yep.
Facing to the broadside, but with small deviations, yeah. So there are four red beams over there, yeah, to the front, to the front direction. Is that a radiation pattern that you really need for HSR?
No, I don't need a specific radiation beam because what I need is I have achieved a sufficient gain. Because firstly, I consider about using circular patch, but as I've read that if you want to have a match impedance, if you want to have an optimal bandwidth, I'm using circular patch. But as I need a very good return loss, VSVR or gain antenna, so I'm using the rectangular patch. So I have now working with the electronic magnetic beam.
Okay, so my concern is that because you are assuming free space channel model, right? And free space channel model is characterized by a single path, yeah, coming from the transmitter antenna to the receiver antenna, yeah, a single straight path. And that means actually you only need one beam, yeah, with high directivity. But now we have four, and with four beams, there could be multiple paths. There could be, yeah. And if we have multiple paths, it's not free space channel model anymore. That's just my concern actually. So I thought there is probably a reason why you design antenna with radiation pattern like that. No?
No,
Oh,
that's the reason I'm gonna need a sufficient gain, that's all.
Okay. Last question from me. So you have a very nice, very interesting shape, yeah, for the design. Yeah, it's like, you know, like two let's say two pyramids, yeah. Okay, or it's like a biconic or something like that. But how did you come up with the shape of that design?
From the books that I have read, because some of them use like just a simple rectangular.
Right.
I have the two books that underline my model like this.
Okay.
And I'm following how to design a calculation and try to configure it.
Okay, that's all my questions. Thank you.
Okay.
Please.
Yeah, thank you, Professor Gamantio. So sharply 20 minutes. Yeah, thank you very much. Then we move to next examiner that will be given to Dr. Irma Zakia. as the MSc. Okay, please, time yours.
Thank you, Mr. Chairman. Okay. Selvi, congratulations.
Thank
Okay.
you, William.
Yes. Okay, my first question, it's related to the, you include in the path loss model also the Doppler shift. Yes. However, we know that in existing systems, already operational systems, we perform Doppler shift compensation either at the transmitter as a pre-compensation or at the receiver. Yes. So this is like an unusual path you took because you include this Doppler shift in the path loss model. So does this mean that we don't need to perform any more Doppler shift compensation at the transmitter or at the receiver because you already include this in your path loss model?
Okay, let me show you about some literatures that I have read about the Doppler and how they compensated in the both transmitter. Let's see. This is some papers that I work out for the Doppler shift compensation. Some of them using like MIMO localization. Okay, here we are. One paper said that this is a mitigation of Doppler effect in high-speed run through relaying. What they are doing is just attaching the moving relays to compensate the Doppler effects. And another one is they are using a fixed carrier frequency because mostly the Doppler cell will destroy your frequency carrier and regard it as a loss of signal. That's why they are using a fixed carrier frequency for compensate the Doppler shift. And also to improve the quality of service of high-speed rail, this is a paper from Professor Boai. He's employing MIMO technologies. He's doing some localization of antennas and repeaters to compensate the. So I mean that the Doppler shift must be compensated like in high-speed rail and also in the base station also.
Yes, of course. And but the path you took is unusual because I mean, so with your path loss model, do we still need to perform this Doppler shift compensation like these papers? I mean, if these papers use your path loss models, do they still need this Doppler compensation? Because, like you said, they use techniques like MIMO localization and so on. So do we still need these techniques?
Because they compensate the Doppler shift by handling the power control. That mitigation is useful for large scale fading. So because and also the Doppler shift has a inversely proportional with the channel coherence time, the velocity. Therefore, it must be compensated because the high speed rail comes with a multi-path propagation and a very dynamic scenario. Even though it is a very small and constant in under Viera scenario, we must have to consider this Doppler shift. So I'm going to put like a really small value that miscalculated with the distance itself.
Okay, so I mean that if I use the technique proposed by Professor Aibo in this paper, but I implement your path loss model, I still need. I mean, I still need to perform Doppler shift compensation.
Yes. Yes.
And why is that? Because you already use Doppler shift in your path loss model. Why we still need?
Because we will never know the very tuned velocity that you've been going through, and also the multi-path propagation that you are traveling to. You will never know because inside the train, inside the train, you will see that they really tune the velocity, including when you are coming to the Viera scenario, you just can speed up, and when you come to the urban, you have to slow down a little bit. That's why actually the Doppler shift will be very fluctuated.
Okay, I mean, it is. I think it is more interesting if you propose adding Doppler shift in your path loss model. Then we don't need to perform any compensation. I mean, because that will extremely reduce the complexity of the transmitter or the receiver. We don't need any compensation because you already put it in the path loss model. I mean, that's what we expect. But actually, you but actually you said that we still need, so there is added parameter in the path loss, and also we still need this high complexity to perform Doppler shift compensation.
Yes, it is a very meaningful insight.
Okay.
Maybe I can do a deeper research about that. Do we need it or not? But accordingly, I have to. I'm really sorry that I have to put it in the link budget because this is a very critical, because it is fully it is dependent on the high-speed rail reliable transmission. So all the losses must be compensated, investigated properly. Thank you very much.
Okay. Yes. Okay. Thank you. Okay. So I would like to go to the second question. The second question is actually related to the ongoing 5G new radio standard for high-speed railway. I just take a note that this is from the 3GPP 38854 release 17. It says that the configuration for the high-speed railway base stations is that the train will be simultaneously served by multiple base stations. So not only a single base station. But from the explanation of the data set that you got from Beijing Jiao Tong University, I believe, or I can infer that the data set is only from a single base station.
I think so, because one set is a given and secondary data set, and actually I don't know which propagation about this, so I make lots of assumption. And the first assumption we initially face when I validate the model, it is correct that for free space propagation, although actually they have conducted some other measurement under the Fielder scenario with the extensive path loss exponent, and with the same scenario they have larger path loss exponent even though they are in the same Fielder scenario.
Okay. So if we assume that the data set is only, the data set is taken assuming that the transmitter is only a single base station. Okay, let's assume
Yes.
that, and therefore you model the path loss model for the Doppler shift effect is like this x3 times the distance, which is a function of time.
Yes.
Because the train is traveling. Okay.
Yes.
And however, if we try to modify, because we know that this high-speed railway standardization is still going on, and if we use this standard in the future, and instead we will the train will be communicated to multiple base stations at the same time. What do you think will affect your path loss model? Which parameters will get affected, or if any parameters will get affected by this
Multiple base station.
5G new radio standard for high-speed railway?
You're gonna have more gain, a very optimal gain antenna to sufficient all the losses. And also 5G actually has many losses, actually, because it's a high frequency and the bandwidth is narrow, it has many losses. But I think if we have more antenna gained, you can all mitigate all the losses, that parameter.
Yes, or perhaps you can show us the path loss model you propose.
Okay, here we are.
Okay,
That's
yes. Okay, that's X1, X2, and X3, right?
Yeah.
Okay. So, this is assuming that the train is only connected to a single base station. And, but in the future, we will have the train connected to multiple base stations. Which parameter, X1, X2, X3 will be, do you need to modify these parameters?
For more base station, the X sigma,
The
Number
shadowing?
2, and the path loss D0 should be considered because this is where the signal is attenuated from the base station to the high-speed rail, and you have to consider to change the path loss D0 values.
So that there will be multiple.
Yeah, for the multiple base
PLD0?
stations. So you will have some more
Okay.
beam, and you can make statistical properties upon this measurement. So the
Okay.
path loss D0 can be varied.
Okay, and why X sigma you need to modify?
X sigma, because maybe for utilization for higher frequency spectrum, you're gonna have more large scale fading and more shadowing. And even though it is going to be compensated with the gain antenna, but you have to consider maybe there is the weather changes or the counter changes. This is where it is all included in X sigma.
I mean, the effect of using multiple base stations, not the effect of, I mean, what does using multiple base stations will affect this X sigma? I mean, do you need to have multiple X sigma or just a single one?
Just one single X sigma, but you must consider to vary the path loss.
Yes, okay.
D0.
So you said one single X sigma, and do you think the optimal value will be lower or higher than the one obtained already in this work?
For the high frequency spectrum, it can be higher, but in X sigma there will be weather changes, something like that. That should be included in X sigma. But if you have a
What does
sufficient
sorry?
gain
What does higher means? I mean, if we have X sigma higher, what does the physical interpretation of having X sigma higher means?
it means that you have more obstruction and interferences. You will have more than because maybe there is a co-channel interferences that many obstruction that you maybe you don't know where it comes from.
Okay.
But it is all summarized.
Yeah, but, okay, X sigma is a shadowing factor, so I don't think it's related to interference. But anyway, I mean, the new 5G NR will connect. I mean, the train will process coherently the received signal from the multiple base station. So it's not multiple base station. One is serving and the other are interfering. No, they are coordinating, and the receiver will try to coherently decode the received signal. So there is no interference issues here.
That is very interesting. Maybe I can analyze it with
Yes.
my other research.
Yeah, so I mean, related to the X sigma factor, I think this is related to the shadowing, right? So maybe you could also see that if we use multiple base stations coordinating, will the shadowing factor increase or decrease?
Yes.
Yes, and also for the Doppler shift, do you think it will be affected by these multiple base stations?
Yeah, of course, because you have an angle between
Okay.
one station, you must consider about that.
Okay, so there will be multiple
Angles.
parameters for
Mhm.
Doppler shift. Okay, okay, thank you. And the next question I would like to ask related to the complexity of the meta heuristic optimization. You mentioned that this problem, I mean, this object, I think your objective is one of the objective is to minimize the mean square error, right? The root mean square error. And usually in optimization problems, we seek to reformulate sophisticated problems, which I assume that I think I once read in your book that this is a nonlinear optimization problem, but usually nonlinear optimization problem can be converted, if possible, to convex optimization. Yes, and with convex optimization, we can have a global optimum, right? So not just a local optimum. And yeah, although I mean, I think there is no explanation about why you didn't try to convert this root mean square error formula to a convex optimization problem firstly, but you just say that we apply meta-heuristic optimization? I mean, is there any particular reason why you don't pick? I mean, you don't try to reformulate it to convex optimization firstly, but you pick meta-heuristic optimization?
Unfortunately, I don't have any reasons for not doing that, because what I'm doing is just I'm observing the minimized error and the visualization of the fitting plots. So I didn't consider about convert it to the complex optimization problems at that time.
Okay. Do you know what is the complexity of the meta-heuristic optimization? Because usually one they don't use convex optimization problem because some problems are not polynomial time. So they use this meta-heuristic sometimes. So do you know what is the complexity of this meta-heuristic optimization?
One thing that why I'm choosing this optimization technique are not choosing the others, because this is based by the target function and the information that I extract from the target function, because the more information you have from the target function, the more easier for you to optimize. And most of engineering problems are multi-criterion and very complex. That's why when I'm only think if that objective function can be differentiated, then I will just do that.
Okay, I mean, you have only 3 parameters, right? So it's not a large number. So only 3 parameters that need to be found here. So I mean, if it's but how long did you take to simulate? I mean, to get this optimal parameter for each algorithm?
I'm doing like 5 batches of iteration for each algorithm, and one batch is like 500 trial times. 500. I didn't count over time. I just count the frequency of it.
Oh, okay. Yes. Yeah.
For GA is really only for GA is really long.
Yes. Okay. So I think it is also interesting to know whether this optimization problem can be converted firstly to convex optimization problem, because before we move to another heuristic ways, because we want to have the global optimal value, not only the local optimal value. Usually we try to do that firstly.
Yeah, that is very interesting. I can do that while I'm using another optimization technique.
Okay. Yes, thank you. And okay, so maybe the last question is related to your link budget calculation. Yes, your link budget calculation is also considers low frequency, right?
Yes.
So this means that you, I mean, your data is for high frequency. So how can you, how can you use the optimum value x1, x2, x3? Because this is optimized for a high frequency data set, not also for low frequency data set.
Actually, from Beijing Kyoto University, they don't tell me what frequency in my data studies. So I really assume the model. They don't give me information. This is for 5G or 4G or something, because at that time the 5G is very secretful for them. So from here, I'm assuming this model can be used for low and high frequency regarding to the antenna gain. And also I have to change the constant first with 32.45, because for low we are working on 900 megahertz.
Okay. So I think this is also need to be, path loss is really sensitive to frequency. If we want to have empirical path loss model, we will need to perform the measurements at that frequency. And I think it is already correct if you fix, like you say that we don't have information which frequency is the data set, but I think you should have one value of frequency to have to perform the optimization. So you can not say that I can use the data set assuming that there is two different frequency. You cannot say that. Yes.
Yes, absolutely. But if the link budget for the, let us see together here. Let's review for the low frequency spectrum. The performance is much better than for the high, if it is compared with the high frequency. You can see it right here, the received signal level for the low frequency spectrum is good. The other one, the high, there is an average number, the mediocre one.
Okay.
But for the low, it's probably for I was given for the GSMR, I think.
Okay. So you don't know whether this is actually it at 26 gigahertz or at 900 megahertz.
But now I know because the receiving level is good in 900 megahertz, while in the 26, I have an average value. But in this part, because it is theoretically more accurate, I have best. But it is only theoretically accurate.
But my suggestion is that because this is a real data set from Beijing Jiao Tong University, you can say that you can assume that this is from 26 gigahertz, and for other frequency you can perform how to say, it's like a frequency scaling. So as simple as that. So you must stick to just one frequency for the data set. So that's the point. So you cannot say that this data set is performed maybe at 900 and also at 26. So you just stick to one frequency. For example, you say 26, and for the other frequency, you of course you can calculate the power link budget just by use frequency scaling and use a different antenna, of course. Yes.
Thank you. Thank you.
Okay. That's all from me, Mr. Chairman. Thank you.
Okay, thank you, Dr. Irma. Next, please allow me to continue and also to give the opportunity to Dr. Auki Widyo Triatmo. Dr. Auki will give the question by online. Okay, please, Dr. Auki, time's yours.
Thank you, Mr. Chairman, and congratulations to Selvi to achieving this level of your study in doctoral degree in ITB. And I would like to ask about first is the you in your dissertation, two models, free space propagation and suburb and urban models are proposed. I would like to know what is the standard used as a basis of design for determining the power link budget and so on in the high-speed rail. So I think there is some standard that is already used. For instance, the models that is used, and I would like to know whether you have conducted the model in the standard and compared to what is you proposed in the dissertation.
Okay, thank you, Professor Ogi. The thing is, why I'm choosing the meta heuristic, because most of path loss predictions is based on empirical models, which is we have to conduct extensive measurement and we combine it with the statistical properties. Many network designers prefer to use this one, although there is some inaccuracies of the model because the performance is really doubtful, because when the propagation is changed, you have to conduct the measurement all over again. Therefore, many of them just jump into the utilization of machine learning because of its accuracy. As I have mentioned before, that by using the meta heuristic, you can find out which parameters that contributes the most. This is where I'm starting for my research. This is where I stand in this research. The standard would be, how am I resolving a very dynamic system like high-speed rail, and there are some parameters that are not and cannot be measured, but I can have the values.
So right now there is no comparison between your proposal and the method that already used by other other researchers or other standards?
Yes, I'm going to show you that the literature is quite limited, but I can show you that I have found a paper entitled Empirical Purpose Models Optimization for Mobile Communication. The author would be the Masoud Garah. He's tuning the COST 231. He's using it with PSO, genetic and algorithmic algorithm. So this measurement is conducted in Batna, Algeria. And in this, he optimized the COST using the PSO, GA, and MIT algorithm and compare it with the original set.
I'm sorry, I cannot hear.
Hello?
Oh yeah.
Hello?
Oh yeah. I can hear right now. So yeah, from that paper, you just seeing that the standard has been compared, and some of methods that you propose closely to what you have done in your dissertation. Is that correct?
Yes, but what the lack of this paper is they don't create their own model because the OST 231 is already existed. What they do is only tuning them with the PSO genetic, another MIT algorithm to show that which better performance between the three algorithms to validate the COST 231.
So the CO331 is the standard
It's a pathless model,
Fatas model.
a pathless model for
That is
cellular.
usually used for engineers to design the power link budget, something like that.
Yes, it is some kind like what is Okumura Hata doing there. They are proposing a model which is utilized in a specific environment. And this one is the OSET 231 is almost the same too. And there is a measurement for COSET 231 is applicable in Algeria, in Batna. So this is where the measurements are taken from.
Okay, so can you perform that method to your data and get the comparison between your method and their method?
In this method, method Garah what has conducted, the tune COC 231 compared to the other models, maybe he's doing it as far as I recall, he's doing it with the Hatta 2 and the COC 231 performed the best.
So you didn't perform any comparison between other methods.
With my model, I created my own model. So there is no connection between my model with COZ 231. In my model, I compare it with like six optimization technique for free space and 2 for two-ray ground reflection.
Yeah. So, but I think we better to compare the result from others with your model, because right now you are just comparing your model with different optimization methods. So I think better if we to add that findings, whether your model can perform better than the existing models.
Yes.
Okay.
I'm gonna make a comparison in another research.
So the next question is how many data that you use in validation, and how do you assure that the model can be replicated in different situation or environments?
The observation range is like from 0 kilometer to 2 kilometer. Comprises is only like 980 perhaps some around that number. Not very much data actually, because the observation range is also limited.
So only one time measurement or many times measurements?
That thing I cannot. Okay, the thing I cannot answer because I was given a secondary data set from the Beijing Jiaotong University in the form of received signal level. So I don't know if they give me from a repeated measurement or just one shot measurement.
So from the data you obtained how many rows if it is a 0 to 2 kilometers? Only one row, one column, or I mean several rows, yeah, from 0 to 2 kilometers, and how many columns?
I think it's like 189 data set comprises received signal level only, it's not the path loss values.
So
That's why I
it
have
is
to
only
break down the received
one
signal
time, yeah.
level. Mhm.
So yeah, so what is the environment in the Beijing Jiaotong University when the data is collected?
That I don't know too, because I assume in my model that the environment would be free space as a typical scenario of high-speed rail. That's why I'm making assumption of this scenario. Meanwhile, if I have broken down in the path loss values, I can assume this is for the free space propagation from the meta-heuristic optimization technique. That it is really comes from the free space propagation as a typical scenario of high-speed rail in Beijing and also in Indonesia.
Okay. So I saw that the model in the beginning of the distance, it is quite far away from the models. Did you recognize that? So it
Yeah,
means that it deviates kind of not linear as in your model. Can you explain about that?
Okay, wait. Okay, let's see one model. Let's see from the GRG first. Okay, yeah, firstly, there is a difficulties to converge like from 0 kilometer to like 250. And then after 250 meter, and then the model start to adjust to the input path loss data measurement, as I can see in this figure 13 right here.
So is it because the model that you choose is a linear model with the distance, with the function of the distance?
There is one non-linear equation, which is a Doppler, and I putting it at very small values. That's why it is actually there is a non-linear component, but because the value is really slow, the curve will look like linear. Because the value of the non-linear equation is very small.
Okay. So there is a logarithmic as well, yeah? Algorithmic function. So so do you make some, so from 0 to 250, do you make some analysis? What is the difference, RMSE or others parameters for the calculating the errors in that region?
The thing is, I'm not calculating the errors in between 0 kilometer to 2 kilometer. What I'm observing is when is the model start to adjust. So I'm not observing about the RMSE parameter during the 0 kilometer to 250.
So what is the actually the next can we say the antenna distance between one antenna and the other?
Assuming this is only assuming this is only comes from one base station and perhaps one antenna to the base station. So I don't think there are some multiple antennas during the journey of this high-speed rail.
Yeah, I mean, what is the usual distance between antennas?
I'm putting like in the paper that I have here. Let's see if we have the same propagation with China, because this data is given from China, we can see it is usually like 20 kilometer from the nearest base station. But let's find out in the paper right here. There is a measurement campaign. Here. In this picture, we can see how the antenna is located. It's like 83 meters from the viaduct to the roadbed. And also, but the receiver to calculate the path loss exponent is located 80 kilometers from Tianjin and the 60 kilometers from Beijing. So actually, I'm gonna assume the same too, because the high speed rail has not been running yet. Typically it's like 20 meters from the viaduct, the base station.
So yeah, it means that the distance between antennas is about 60 to 80 kilometers.
Yeah.
So it means that the deviations from 0 to 250 meters will not be very in our consideration, right?
Yes.
So how about the so because your data is only 2 kilometers and it seems that it starts to deviate after 2 kilometers, and it deviates, it means that it is going larger, then how can we assure that we have the right model for just 80 kilometers?
Okay, I assume this is what I make an assumption too. Between the 2 kilometer, I assume the path loss D0 would be 250 meter from the base station. This is where the signals begin to attenuate from the base station. This I assume to be put in my model, because when this model is designed, we are not ready for the high speed rail. And what I have from the Beijing Jiaotong University is a receive signal level. That's why I have to extract the receive signal level and design my own model for high speed rail. So the 240, which in this case the path loss D0 comes from the D by D0, comes from the assumption, my assumption.
Okay, so we actually, but how your methods probably will be used for expanding from 2 kilometers to until 60 or 80 kilometers?
Okay, in the link budget that I'm using, you can just clicking the buttons and put the kilometers that you want to travel with. And then after that, we can observe the receive signal through the link budget that I have presented in my slide. So perhaps for more data set can achieve the nearest adjustment too.
So what is the path loss decibel that is allowed for the signal to be traveled?
Yes, typically for free space is 2, but you can see in this paper, even though this is the same propagation, the same viaduct scenario, under the measurement we can achieve the path loss exponent 3. under the same environment because of the train roof causes distortion in the antenna radiation. But in the meta-heuristic technique, since it is theoretically, I put initially 2, and when it is iterated, the Patas exponent is averaging, and I achieve the same value, which is 2 also.
Okay, so I would like to ask the last questions. New buildings and trees in Indonesia may grow in the middle of the signaling path. So what will be the impact if this happen, and what suggestion should the operators to keep the designs as close as to the free space assumption?
Okay, firstly, the proposed pathos models can be utilized to accurately estimate the channel modelings of large scale in high-speed rail. So modeling budget can be usable for the network designers in deploying base station infrastructures, or helping them doing the planning frequency tags or small stage coverage. So when you can just put some parameters in the modeling budget, and if you click calculate, you will know the receive signal level in the train is estimated like good or average, and then if it is good, you can just proceed with the field measurement.
Yeah. So, but I mean that you are still working with free space, right? But
Yes.
in the reality, we see that Indonesia is a very not disciplined in the sense of there are growing trees and new buildings in the place that it is not allowed, probably blocking the signaling path. So what do you suggest to the operators?
Okay. I suggest to the operators, instead of using my power link budget, you can validate the link budget by using the extensive measurement to validate my link budget, because for myself, I really want to continue my research by doing another measurement for our propagation in Indonesia, because there would be a change of path loss exponent dependent on the multi-path propagation.
Okay, that is all my question, Mr. Chairman. Thank you very much.
Thank you, Professor Ogi.
Okay, thank you, Dr. Ogi Widyo Triatmo. Next, we would like to move to promoter team. Firstly, I would like to give the opportunity to Professor Buai. Professor Buai, PhD from Beijing Jiatong University, China. Please, time yours. You have 10 minutes.
Okay, I have just 2 questions. One is, what do you think about the modeling performance compared with the existed path loss models? Okay.
Okay. My model is extracted from the dynamic system of high-speed rail, while the other model is located in a steady environment where we have some kind of precise parameters. But I think for the running high-speed rail with a very dynamic velocity, either you have to choose machine learning path loss prediction, or you can do like meta-heuristic optimization. So the difference is it is dynamic or steady.
Okay, the next question is, have your developed channel model been used in high-speed railway? For example, from Cikarang-Bandung high-speed rail.
Excuse me, can you repeat again about your question?
Have your developed channel model been used in high-speed rail, in the rail engineering application?
Yes, I hope that my model can help to accurately predict the large-scale channel fading in high-speed rail Jakarta-Bandung, as the link budget is readily to be utilized. So perhaps by using the link budget, we can know the receive signal level in the train to help the network designers in deploying the most optimal base station infrastructures, or designing a small cell coverage area, or even the frequency planning if we will gonna use a new frequency.
Okay, I suggest that in your future research, you should make a deeper attention on about the AI-based channel modeling and channel prediction. It is a very important and interesting work. Okay, thank you.
Yes.
That's
Yes,
all.
thank you, Professor.
Thank you.
Okay, thank you, Professor Buai. Now we move to Professor Insinyur Indra Julianto, PhD. You have 10 minutes.
Thank you, Chairman. Congratulations for your dissertation defense. And there's my question. The method that you propose, this is usually called as a gray box modeling. Compare with, suppose we use the machine learning, which is based from the data, and this can be called a black box or modeling. In the gray box modeling, it relies on how we construct the structure of the model, because it will determine the accuracy of the result. So in this case, I would like to ask, how do you justify the component that you construct in the model?
Okay. Let me review a little bit about what is the gray box model. The gray box model is a modification between the white models and the black box model. In the white models, we have a complete parameters. We can observe the physical parameters, physical phenomena, and they are all complete. Meanwhile, in black box model, we only have data sets. The machine learning the machine learning prediction is included in the black box model. In my research, I have some physical phenomenon parameters. I also have a data, but this one is complete, and this one is not complete. This one is complete. That's why in this case, I'm using what we call the gray box model, and the gray box model, if it is applicable appropriately, it can resolve many things. For example, for many engineering complex problem. In my research, in the physical phenomenon, we can see that there are 3 unknown parameters from the physical phenomena that actually to attain these values are almost impossible from the running high-speed rail. That's why the utilization of gray box model is most suitable to be utilized in this research.
I mean that justification of each component in the path loss model that you use.
I have defined all the parameters. I have defined all the parameters priorly in here. And this is the path loss from the path loss model. This is the physical phenomena that I have observed during by reading literatures. And this is how I justify my parameters. Let me see. Okay. Each parameter has a special contribution that must be included in the model. For example, the unknown parameters x1 must be included because this is, as I have mentioned, this is where the signal is begin to attenuate. And also I justify this x sigma because when there is a factor of weather or uneven counter, it can be some parameters in the x2 and also the effect Doppler. And then after this, we have a complete parameters, and only these 3 we don't know the values.
Okay. Now I would like to go to the second questions. I think you found the models like you show in this PowerPoint. So what is the benefit of this model?
Okay, I hope these models can help accurately predict the large-scale channel estimation for our upcoming high-speed rail of Jakarta-Bandung. Because you can observe from the link budget the received signal level that is received in the high-speed rail, you can determine if whether the signal level is quite strong or average or just mediocre. So whenever this is mediocre, you can just click some parameters. Here, maybe you have to add the antenna gain. Maybe you just have to play with the Doppler, or you have to like increasing the antenna height or something like that. You just can click the button in my link budget.
I mean that your model is cover a broad range of the applications.
Yes,
For
it is.
the Jakarta Bandung case,
Yes.
it's already put is on above all the obstacle. So what is the benefit of this model?
This is the model will be usable if you want to integrate with the higher frequency spectrum, because there is a button for putting higher frequency here, because outside Indonesia, the frequency is already integrated to 4G LTE or 5GR, even though we are still using 900 megahertz for GSMR. But I really hope that it can help for the network designers then. The propagation in Indonesia, they are mimicking what they have done in Beijing. So in Indonesia, we don't know what the propagation, what the scenario, it is not still running yet. But I really hope the link budget can be made into use afterwards.
Okay, that's all my question. Thank you, Chairman.
Okay, thank you, Professor Indra Julianto. Now, last but not least, the last question will be given by Professor Dr. Insinyur Jul Junaswin as Chief Promoter. Time is yours.
Thank you, Mr. Chairman. My question is, you mentioned that you are using so many optimization algorithms in your works. Any specific reason that you use these methods? Because we know that there are so many optimization algorithms, meta-heuristic, especially in the literature. So can you mention any specific reason why did you choose these methods?
Yes, I think when you have to choose which optimization technique which is appropriate for you, first of all, you have to observe your situation. You have to observe really well your problem and your target function. Because more information you have from your target function, the more easier for you to optimize. That's because you see, for many engineering complex problem, when working in a large sample, it can work really well. But for the finite sample, it can produce some bias. Therefore, what your consideration in choosing which optimization technique must be under consideration of whether the objective function can be differentiated or not. And it is depending on your problem and your situation and your observance to your parameters.
So how did you determine the objective function for each algorithms? Because there are many ways to determine this. It depends on the data and the objective.
As I'm in my case, what I need is to minimize error. So if I have a very minimized error, that means my output data path loss from the proposed path loss models can close to the scenario dynamic from the input path loss data measurement, which means it seems like one line, which means a very minimized error. That is my objective function. So in my thesis, I have to minimize my errors.
Did you use the same objective function for all the algorithms?
No, it's just minimizing errors.
Minimizing errors. Okay, so thank you for the next questions. You know that the Indonesia will use the high-speed railway, Jakarta-Bandung, in the next few weeks, I suppose. And I assume that we can use your formula to be implemented in this high-speed railway Jakarta-Bandung. So what is your suggestions to the government, to the KCIC, or to the KI, in considering that this railway tracks between Jakarta Bandung is not so easy. It has so many tunnels. It has also it runs on very high, and also many well, like not like in China probably and other countries. Do you have any suggestion to the government or to these parties how to implement this? And what is the consideration you would propose to them to implement your formula, or your formula has to be modified to be adjusted with the local condition? You know, Indonesia, the weather is also in tropical areas. And how do you consider this weather condition in Indonesia, for example?
Okay, to answer that, let me show you from my link budget over here. Let's see the link budget here, but priorly I'm going to answer you about other scenarios, such as, for example, tunnel. In a tunnel scenarios, what we can do is making another extensive measurement by using ray optic measurement or signal excitation. Because in the tunnel scenarios, there will be Wi-Fi all over along the tunnel. And also for other scenarios, you can do like field measurement again, field measurement, not forget to mention that you cannot collide with the frequency carrier. But what I suggest, really proud if the mailing budget can be used in high-speed rail in Jakarta Bandung, because when the network designers want to do this and they want to know what is the receive signal level on the train, they just can put this parameter here. If you want to have a receive signal level, they can increase the gain or change the antenna height, or even changing the frequency that when you are working for. And by clicking like this, they can have an optimal receive signal level. And also whenever we must face for a severe condition of weather or contouring, the sigma can be included. They can make a measurement of the path loss, the loss of signal because of the changes of weather, and can be put in the X sigma, or even the Doppler frequency. Maybe they can measure how much the decibel frequency, and they can put in here and make a simulation to have these values. And after we calculate, they can have the value or receive signal level before they conducted the real field measurement. And maybe they can compare it in the field, and in the simulated it is like this. So it can help them to do some frequency path planning and more additional small coverage area.
Okay, I missed some information regarding the weather condition. How did you take this into account in your formula?
Yes, the weather condition may cause this signal distortion and the frequency distortion also. That's why I'm putting in the X sigma right here. Because many disturbances will come along the way, not just weather. Maybe an uneven steep inclines may cause disturbance. So that's why I'm summarize it into one parameter, what we call the X sigma right here.
Are you sure that it can be implemented, the formula in Indonesian railway, high-speed railway?
Yes, it can be prevented, because once you have these complete parameters, and I think it is most complete regarding it's only one base station that cover this high-speed rail, you can have achievement for receive level. You will know the receive signal level. So you can compare it. If it is simulated like this, you can like, what about in the field measurement? If it is good as in the simulated, you can just proceed with the development.
Okay, then you will have a very future works for the next Indonesian railway, high-speed railway. Thank you.
Thank you very much.
Okay, thank you, Professor Jules Naswin. Ladies and gentlemen, we just completed the first session of the dissertation defense. And then I will ask your patient to give the opportunity to graduate school commission to conduct evaluation meeting. Then I would like to suspend this session approximately for, I think in between 15 and 30 minutes because today is Friday. Okay, thank you.